Okay, I think we are ready to start. So it's a real pleasure today to introduce Alon Halevy from the Recruit Institute of Technology, who had this very distinguished career, which started basically with PhD from Stanford University in '93. Then he went to Washington University, where, of course, after a while founded a database group, but then he started getting to starting company. Started the first company in information integration, and then a company in working on deep web retrieval. That company was bought by Google, so it became a Googler for about 10 years, right? It just got this new position 2 months ago, and perhaps we'll tell you more about. But he's also a kind of renaissance man, because besides his book on principal data integration, he's also well known for his book on the infinite emotions of coffee, okay? All right, so before we finish welcoming him, also to mention Dr. Norman Friedman, after whom the lecture is named, who was also a UCLA alumnus, and he covered a number of important jobs as Secretary of Defense, and then, of course, he also worked as founder of several companies. The most important attribute, of course, is that he is a generous supporter of our department, and particularly he's been the donor of the Friedman Chair in Knowledge Science, which I have the privilege of occupying. Okay, so please greet our speaker and our donors, and a great hand of applause. Thank you.
Thank you, Carlo, and thank you for having me here again. Actually, I was here 12 years ago when some of you were in middle school. Most of you were in middle school. Thank you for mentioning my coffee hobby, because you'll see it in a lot of the examples in my talk. One thing I can tell you about coffee is if you're going to talk to an Italian guy about coffee, make sure you have a lot of free time, because they're going to have a lot of opinions and you're going to get into a lot of trouble. So you're probably, Carlo invited a guy from Google to come give a talk here, and he got a guy from this institute that he never heard about. So I should probably explain what it is that Recruit does. Recruit, and I'll spend 2 slides on what this new lab is about, and hopefully you'll see throughout the talk that some of what we did at Google will actually transfer over to RIT. The way to understand Recruit is we have about 200 sub-companies or subsidiaries. If you look at this column on the right here, these are companies that you've probably all heard about. So Recruit owns the same thing, the equivalents in Japan. So any life decision, big or small, looking for a job, looking for a bride or a groom, getting your wedding done after you've actually made that important decision, looking for a new place to live, buying a car. These are all decisions that are supported by services of companies of Recruit Holdings. It's the majority of it is in Japan, but the company has also bought a lot of subsidiaries in the US and Europe and Southeast Asia. So some of you may have heard of Indeed.com, which is the biggest job search company out of Austin. That belongs to or that's owned by Recruit. So it's a lifestyle company. It's a company that knows a lot about what you're thinking about, what are the kinds of decisions you're making on a daily basis, or the big decisions. So the Recruit Institute of Technology is a new institute that is now formally headquartered in the San Francisco Bay Area. Location to be determined in the actual office location is being determined even as we speak. And we're going to be doing a broad spectrum of research in the intersection of AI and data management. Okay, so you have data on this side, you have insights on this side. Getting from the data to the insights requires a lot of data management, like operation, visualization, preparation of data for applying machine learning algorithms. So that's a pretty broad spectrum of what we're going to do. One of the interesting questions that we're going to ask also in this lab is, given that this is a lifestyle company, one of the questions we're asking is, can we actually build technology that will make people happier? There's actually a lot of work in the area of psychology called the science of happiness. So we actually know with science what actually makes people happier in a long and sustained way. And now the question we're asking is, can we actually use technology to steer people towards behaviors that make them happy. So if that makes you happy, you should come and consider working for this new lab. In terms of the philosophy, I'm stealing the philosophy of Google Research and I'm importing it into RIT. So we're very much embedded with our subsidiaries. We're going to be contributing to the company as our first priority. We're going to be writing publications in top-notch venues, and we're going to be contributing to social good. So we might create open source tools, we might create digital artifacts that are of general use for society. We're very excited about that. If you actually want to hear a little bit more about the trade-offs, or at least my thoughts about 10 years at Google and how to choose projects at a research lab, I wrote a Sigmod blog a few months ago, aptly titled "A Decade at Google," which talks about some of these ideas. But that's not what I'm here to talk about today. Today I want to talk about one of the most important trends in web search. And web search, when it started, was basically a list of 10 links, right? You put in a query, you got 10 links to web pages, and a lot of the work for 15 years went into making sure that those links are relevant and they're ordered so the search engine would do the best job to give you the most important link first. But as of about 4 or 5 years ago, search engines realized that the world is not just a bunch of, or the web is not just a bunch of web pages. There are actually entities in the world. Okay, these entities can be people, companies, places, artists, stuff like that. And these entities have attributes. And a lot of the time when people ask queries, they ask a significant number of queries are about entities and their attributes. And furthermore, when people ask queries from their mobile devices, they don't want to get a web page, they want to get an answer. So a huge trend, a huge effort in, I can speak for Google, but it's true for the other search engines, has been on building these knowledge bases that have this very broad set of facts about stuff that people are interested in, and making sure that queries that come into the search engine using just keywords, just like before, so the user shouldn't have to do anything special, can get answered using these databases. So today, you can query for somebody like Mike Stonebreaker, our most recent Turing Award winner and a member of our database community. And you get this is called a knowledge card on the side. You get a photo, you see what it is, a few sentences from Wikipedia, how old he is, and a bunch of other awards or other information about him. That's an example. You can also ask about attributes of people. So you can ask about the wife of the entity Barack Obama. Okay, so the search engine in this case is smart enough to realize that you're not only asking for an entity, there's an entity in here, but the other word in the query is actually an attribute. You could have asked for spouse, you could have asked for wife, you could probably ask this in Italian and also get an answer, and the search engine understood and gave you the right answer. You can ask for sets. So for example, Woody Allen movies. It's a set of movies. So first of all, it identified that you're asking about movies, and the search engine identified that the movies that you're asking for are directed by Woody Allen, or actually in this case, either directed by or he played in them with. It turns out with Woody Allen, it's about the same thing. But it gave you a very structured answer. Okay, so these SQL queries are getting more and more intricate. Here's a query that I asked about a month after leaving Google, so I can say I'm blown away without appearing to be biased. I was in Seattle one Sunday morning, and I needed to go to a T-Mobile store, so I asked, actually using voice recognition, I asked for the T-Mobile store, downtown Seattle, Sunday opening hours. If you had to write this in SQL, this would be pretty complicated and probably a good exercise for your undergraduate database class. So you have, first of all, I'm asking for a T-Mobile store. That's probably the entity. Downtown Seattle, I'm not even telling you, that's a fuzzy term, right? I'm telling you Seattle, but it's downtown Seattle, which is a little bit more prescriptive about what I'm asking for. And I'm asking you for opening hours, and I'm asking you for the Sunday opening hours. Okay, so those of us who revel in relational structures realize that this is like a very nested, if you had to represent this is a very nested structure. And kaboom, it gave me the right answer. Okay, I did not do this. I was just blown away. I still didn't go to the store, but I was impressed by the answer. Okay. I asked for downtown Seattle.
The one that it returned you, do you remember? Downtown Seattle, or did it return you just a general one?
I think when I checked, it was actually the one in downtown Seattle. Yeah. Later that day, I went to the University of Washington to show a bunch of people the beautiful cherry blossoms that you see there, except that I was in the middle of November. And there are no cherry blossoms in the middle of November, and I was standing there with my Japanese guests, and I was like, believe me, in March, this is beautiful. So what I did was I talked to my phone, I said, images of cherry blossoms at the University of Washington, and then kaboom. Okay, so it understood that I'm looking for pictures of what's in the picture, where the picture is taken, and it actually gave me the plaza where it's best known for the cherry blossoms. So these are queries 3 years ago. If you would tell me that any search engine could answer these queries, I'd invite you for coffee. But I mean, this is pretty amazing. Okay, so these are complicated queries, and they require a lot of understanding and of structured data. Turns out, structured data can also be funny. So apparently one day we had in our knowledge graph, we had the height of Stephen Colbert in an inch less than what he perceives to be the truth. Okay, he made a huge fuss about it in his nightly show. You should actually watch the video. It's really funny how he really 1 inch of height means so much to him. So a special committee got together at Google and figured out an answer to this. And for a few days, if you would query how tall is Stephen Colbert, you would get this this answer, which has the right answer. And all he really wanted is to know that Jon Stewart is shorter. Okay, so apparently, who knew structured databases can be funny? I'm sure every database professor here thinks that way. So the point about all this is not your traditional database. What Google and other search engines are doing is they're answering a structured query from a database, but it is different in many fundamental ways than a traditional database. For those of you who don't have this imprinted into their brain, this is what a database looks like. Okay, a database, first of all, is about a single domain. It's about courses and universities and teachers and students. Okay, so you're already throwing out 99.9% of what people care about in the world in your database in order to create a schema. Then you're creating this schema, right? The names of the tables and the names of the columns, right? And if you don't put the data according to that schema, the database it'll throw you away. We call that a feature. When you go to the real world, that turns out to be a bug. And then the queries are written in this language that is gorgeous, right? I mean, it's called SQL, and once you get familiar with it, you can't imagine life without it. But nobody out there in the real world wants to learn this query language. So what Google is doing is answering database queries by throwing out all the assumptions that any database person was trained to look at. So let's look at that. Okay, so let's look at from two perspectives: the data and the queries. Okay. So first of all, the data comes from all kinds of places. It's not like you have one store with one schema that has all your data. The data is coming, a lot of it is coming from the knowledge graph, the Google knowledge graph, okay, which is a triple store of facts about the world, which originally comes from Freebase, and Wikipedia. But it also comes from other places like HTML tables. So if you look at this query, you're asking for what was the first state to join the Union. There is a table out there, an HTML table out there on the web that somebody created that tells you exactly when, what order the states of the United States joined the Union. So here, what the search engine is doing is it's not going to the knowledge graph, not because it didn't want to, probably because it couldn't map that query to some content that exists in the knowledge graph, but it did find a table out there on the web that it doesn't completely understand, but using techniques that I'll tell you about in the next in part of this talk, it figured out that this is a good answer to your query. Okay, there are other ways there are other sources of structured data that exist on the web. One of them is there are many like this. Google Fusion Tables is actually one of the projects I spent most of the last decade at Google. The idea of Google Fusion Tables was to create a database system that real people can use. Okay, so people who care about data, like journalists or activists in a particular domain, people who care about water cleanliness or refugees. And these people don't have a database expert sitting next to them. They can't afford a database expert. So what we did was we limited the kinds of things that you can do with a database system so that you can upload data, create visualizations very quickly, tell stories about that data, and publish it on the web very fast. This example visualization was actually created after the earthquake in Japan in 2011. I think it shows shelters, where there are going to be shelters in the affected areas. This map got something like 100 million page views a day for about a week, and probably helped a lot of people in need. There are other products like this today. The data can also come from text itself. Okay, so Google, the search engine might actually find that the text, if using information extraction, you can actually find good answers that are structured data. So the other things the search engine needs to worry about is, first of all, you can't just give any answer, right? And this might come as a shock to you, but not every fact on the web is true. Okay, so I'm sorry to say that. And so Google or a search engine will only display a fact very prominently if there is some corroboration. Okay, for example, a fact will only go into the Google Knowledge Graph if it can be found in 3 different supposedly independent sources. That's what happens when you get a lawyer in the room. Okay, 3 is the magical number. Okay, so you have inaccuracies. You have the world changes. The web doesn't change as quickly as the world. So the search engine needs to be concerned very much with the quality of the data that goes on. When you have an SQL database, hey, whatever tuple I can find that satisfies the semantics of the SQL query, you're getting it. Okay. The other challenge, which is actually subtle but huge, is you don't have a schema. Okay, people ask queries about every topic they care about in the world. Okay, it could be about Barack Obama's wife, or it can be about the birth date of Fahrenheit. Okay, so there is a partial schema. The knowledge graph does have a schema, but the queries need to be the data is going to be about everything. So if you're going to come with an approach of I'm going to build a schema first, you're going to lose a lot of data. Okay, and even if you had a schema, try to translate it to 100 and something languages. If you look at the queries, well, you don't get any discounts. So users, just because you're trying to answer queries from structured data, they're not going to give you any discount in terms of how they're going to pose their queries. So they're going to give you keyword queries, and the important thing about that is they're going to use the words that they have in their mind. They're not going to learn a schema and use the words that are in the schema, which is what a database system requires from you. So you better be ready for all kinds of variations on how to query for the same thing. In fact, you don't even have to be very smart. You can be an ignorant American and ask for who is the king of Denmark, and Google will very politely tell you that Denmark actually has a queen, not a king. Okay? So you can be completely off and sort of, yeah, there is a monarch there. I think it's a king, but Google will fix it for me. Okay? Answers need to be objective. Okay, so you can't, Google is not going to tell you how many nuclear weapons any North Korea has or anything like that. So the knowledge graph is very tailored to very objective data, which limits the number of queries that you can ask, because some people want to know, give me the list of cute animals. Okay, Google should be able to tell you that puppies are cute and rats apparently aren't. Okay, maybe this will create a new world, lead to a new world war, but probably not. Okay, so and this is a question that Google has not yet answered, but it is a limitation. So, for example, if you're asking for the boyfriend of Taylor Swift, you're back in the 90s. You're getting 10 links, and you're going to have to figure this out by yourself. And I actually know nothing about Taylor Swift, about her situation. Okay. Here's another interesting thing about queries. The answer provides context. In SQL, in a database, when you ask an SQL query, you're getting a bunch of rows back. Okay, these are the rows that satisfied your query. You should be thankful for that. On the web, you're getting more. So you're asked for where was Fahrenheit born? Apparently Fahrenheit was born in Poland, but he actually lived most of his life in what used to be the Dutch Republic. Okay, so here the search engine is actually giving you a little bit of context of your answer. Okay, it would be nice if I could say, well, Google figured out that he was just born there, left when he was 2 years old, and went to the Dutch Republic, and really wants to tell you that, but that's not what happened. Okay, Google is basically giving you a little bit more context about his life, which probably actually gives you a better reply to your information need rather than the specific date. Okay, so that's interesting. In database theory, database practice, we have no concept of what it means to give context around the answer. What might the user actually also be interested to know in addition to what they actually explicitly said in the query? Okay. The other thing that search engines do, just by lack of infinite resources, is focus on the head queries. So if you're going to build a search engine, you're going to put effort into answering queries from structured data, then you're going to prioritize the topics that you're going to deal with. And so you're going to look at what are the queries that are asked to the search engine most frequently, because that's where you're going to get the most bang for the buck. But as you know, in web search, a lot of the queries are tail queries, meaning you see them, I don't know what percent it is today, but sometimes it's 50% of the queries are under the radar. But together, they're a huge percent of the queries. So you're losing, when you're focusing on the head queries, you're actually losing on aggregate content quite a bit. So that's the context of my talk. What I'll actually talk about today are 2 projects, maybe 3, maybe not, that we did on our team at Google over the last decade. Okay, one of them is what you saw appear in web search results is actually answers from HTML tables on the web. And the other is Bipropedia, which is an attempt to mine the long tail of schema of stuff that people are interested in from the query logs and from text. We did some work on mining subjective facts about cute animals and the fact that rats aren't that cute, but I probably won't have time for that. So let's start with, and by the way, ask questions anytime you want. Yeah?
What does it mean when you ask about the store, the T-Mobile store in downtown Seattle, that Google had 19 million with something result? How many stores?
What that would refer to is actually the number. So Google gave you a structured answer on the top, okay, but then it also gives you a bunch of links, okay? And so this is a historic thing at Google that we will, no matter, even though you will never look or rarely look past the answer number 10, you still like to know that you're going to get 19 million results if you really wanted to. But it has. That means that there were 19 million pages in the Google index that could be considered relevant to your query, which is really of entertainment value only. In the beginning of the web, right? You ask the question, especially vanity queries. You ask you ask for your name, right, on the web, and you find that there are 17 pages on the web that mention you. You're feeling good, but today it's really historical and entertainment value. It's not. I mean, yeah, you can browse through them, but I'm sure there are better ways to use your time. So, web table. Any other questions at this point? Okay. Yeah. So the question is essentially, you'd like to know that the answer is true, not just corroborated. In fact, As long as it's true, you don't care whether it appears in more than one place, but 3 places might have it all wrong. And so just the fact that it's corroborated doesn't mean that it's true, right? Now the problem is it's very hard for a search engine to actually look for real truth. Okay, all we have is an index. We have pages. Now there are pages that we believe more, right? So you can say the population of a country. If you find a page on the government site of a particular country and it mentions the population of that country, well, hey, they know, right? That's the government. Actually, it turns out not to be a very accurate source. But there's just no practical way to authenticate a particular answer. I mean, we do have people looking at actual triples that go into the knowledge graph. We can't have enough people to look at every triple that goes into the knowledge graph, so or any fact that goes into the knowledge graph, which means that we need to get a big enough sample looked by people in order to put it in the knowledge graph. The corroboration is kind of the corroboration means that you've seen it in multiple places, but it also means that you saw it in good places, okay? Places that are actually ranked high by the search engine. So yeah, it is possible to game the system to have 3 really good sites that are otherwise, very frequently visited and give a lot of good data, and they're all wrong on a particular fact. But the nature of the world is such that if 3 or if multiple very good sites agree on a fact, then it's probably true. But yeah, no, it's not truth that we can authenticate. Okay, so let's start talking about web tables. So this is an example of a web table. It talks about current National League, Football League head coaches, or probabilities of events in poker. So we all see these tables all the time, right? And sometime in 2007, Mike Caffarella, who is a professor now at the University of Michigan, and I started asking the question of, how many tables like that are there on the web? And are they useful? And one of the nice things about working at Google at the time was you can answer at least the first question in an afternoon. You write a MapReduce, you run it over the entire Google index, and you get an answer. That satisfies the curiosity to a certain point. This was 2007. We ran it on the English part of the Google index, which at the time was much smaller than it is today. The answer was 14 billion tables. Okay? Don't get too excited. Okay? The vast majority of this is junk, but I'll talk about that in a moment. Then the question was, can we actually find the good ones from the bad ones? And does anybody care? Yeah, we're database people. We get excited seeing in 5 orders of magnitude more tables than anybody else. But will anybody in the real world care? Okay, so we started this as a summer internship project of quite a few interns in 2007. Some of the interns that worked on this project in 2007 are now tenured professors. And then we had a bunch of launches after that. So the general strategy was you go on a web page, you find, right, HTML has this HTML a table tag, right? You check table tag open, table tag, close table tag, you count. The simplest MapReduce you can imagine. And then you have to apply heuristics or some technique to figure out which are the good tables and which are the bad ones. Okay? Now the sad news is that less than 1% of that 14 billion, those 14 billion tables are what reasonable people, meaning us, would consider high quality data. Not anything having to do with truth or not truth, okay? You can have bad data but formatted in a nice way with meaningful semantics, and we'd count it as good. But there's something very nice about the number 14 billion, which is even after you throw out 99%, you're still left with a lot of tables, okay? So at the time, we had 154 million tables left after all our studies, and that was about 5 decimal or orders of magnitude more than any other database in the world. I think it still is. And of course, it has no schema. It's about everything in the world, and so it's a great playground. I mean, as a database person, you could not Imagine having more fun.
How detect a bad table? Why do people generate those tables?
Okay. So people are not malicious. Okay, it's not that people said, Alon Halevy and Mike Caffarella are going to start this project. We're going to spam them so they can write not one paper but 3 papers. No, that's not the case. Okay, what happens is HTML. Sorry, I should have said this. HTML tables is the only way in HTML that you can actually arrange things in rows and columns, which means that if you're trying to create a calendar or you're trying to organize things a little more, in rows and columns just for formatting, you're going to put things in an HTML table, and that is the biggest use of HTML tables in practice. There is a way in HTML to say this is a header row. Okay, so that, I forget the code word for it, but there is a way of saying this is a header row, which probably would indicate that you're thinking of some schema and maybe there's actually data there. But guess what? Nobody uses it. Okay, so this is the prime reason that that so many of the HTML tables on the web are not what we would call high quality content. Okay, so just going back to what the challenge is. So you can say, well, let's use machine learning in order to build a classifier that will tell you what are the good tables and what are the bad tables. But when you're working with data that is 99% bad, okay, then any machine learning algorithm that will always say no is a pretty good starting point, okay, and it's going to be really hard to beat it. So you need to do something a little different. So these are examples of easily removable bad tables. But sometimes, we had a bunch of database PhDs sit in a room and look at a lot of tables to see whether we agree on whether a table is a good table or not. And the answer is no. It's sometimes very subjective, and it depends on how much, what kind of beverages we just had before the discussion. And so here, this is somebody's preference on music. Okay, so this is one person, possibly the audience of himself and his 3 friends, and the list of Pokemon by base egg cycles. I thought this was obscure, but now that I have a 10-year-old, I'm thinking this is pretty important. But but right, it's just a matter of perspective, right? 2 years ago, my son didn't know about Pokemon. I couldn't care less about this thing. So it's very subjective what is a good table and what isn't. And when you're actually trying to do an evaluation of your algorithm, you find out that even experts disagree. There are a lot of tables that are what they would cause a database person either a midlife crisis or a really bad ulcer. So here they took this is a table, right? Except it's transposed. So the first column is the name of the attributes, what we all teach to be at the top, right? That's a schema. And the second column is basically the values, but it's talking about a single entity. So here you're talking about the Walt Disney Company or the Asilomar Conference Center. So it's one row, right, in what we would call a table. But except these tables are replicated, they appear in many pages. And so if you put them all together, that would be great. But as one 2-column table, you could argue whether it's useful or not. They actually did turn out to be useful, but you have to treat them in a different way because the schema is a column and not a row. Turns out to be that way. So we went through a lot of pains and sweat in order to figure out how to find the good tables from the bad ones. Okay. And I think, there are some obvious things that you can do, like looking at some regularity, try to guess if there's a first row that is a schema. But not everybody thinks schema is important. Sometimes you have beautiful tables that a human can understand, but there's just no schema row there. But to me, the most important lesson from all what we did was we tried to find some semantics in the table. Okay, if we could find some semantic signal in the table, that was by far the best thing we could go on to realize that there is actually good data here. So, for example, look at this beautiful semantics. So, if you see a column like this has a bunch of, so even before going through this animation, you see a column of values, okay? You can take these values and map them to the Google Knowledge Graph. These are all states in the United States, okay? So the fact that you have a column that all the values belong to some class that you recognize is already, that means that you have some semantic happiness going on in this table, okay? That's a better clue. These are not random strings taken from completely different things that are unrelated. So if you can find such semantic signal, then that's a really good clue that you have semantics. So obviously Georgia will give you problems because Georgia is actually a state and a country, and New York is a city and a state. But given that you have a whole column of these, you can say, well, most of these are actually mapped to a state, so I'm going to resolve the Georgia to a state and the New York to a city, and be able to figure out that this is a column of U.S. states. Okay, but this is again, trying to recover semantics is the most important lesson that we came back with from our work. So how do we do this? We had 3 steps basically. First, we wrote a bunch of handcrafted rules that got rid of 90% of the bad stuff. Okay, awesome. Then we had another decision tree classifier that what it did was it focused on high recall. So we still accept a lot of bad tables, but at least the proportion between bad tables and good tables is getting closer to each other. And then we applied an SVM classifier with labeled examples that were taken from the output of the second step. And bottom line was the precision was good enough. Okay, not perfect by any stretch of imagination, but good enough. So then what do we do with it? We did 3 things. Okay, first we implemented the dream of every database person, a search engines for tables only. Okay, can you imagine? I mean, this is like, I can imagine. So if you go to research.google.com/tables, you will find this wonderfully architected artifact, and you'll see that you can search for, what are you searching for? Coffee, right? So you're searching for coffee exports, and you see that it came up with a bunch of tables. Okay, for a while this was the most queried query on the search engine because that's what we optimized for. But you can see that we get answers with relevant tables, and we have you can import these tables. So you can now take this table and import it into Google Fusion tables or into Google spreadsheets and start working with it, which gives you sort of an ecosystem of happiness. So you found the data, now you can start and do stuff with it. After that, so we did this. We were very happy. We had a few thousand queries, 10,000 queries a day for a while there. But apparently the world isn't as excited about table search as a bunch of database PhDs. The Google Docs folks came to us, and Google Docs has this research tool. So today, being a student is actually easier than when it was when I was young. Okay, if you're like writing a paper about something, say you're writing about Abraham Lincoln. Okay, so you're writing something, and now you want to put in an image of Lincoln. Then you can do a search in Google Docs. You can do a search on Lincoln and drag an image into the doc. If you want famous quotes, you do that. Well, so now you can do this with tables. Okay, so you actually want to appear intelligent. You're writing something about coffee exports of countries in the world. You can do a search on tables on our table search engine, get a table, and you can just plug it into your document, and now you're looking so much smarter. Okay, but the real goal, which took a few years to realize, was we wanted tables, HTML tables, to come up in Google.com search results. Okay, because that's the holy grail at Google, and if you can do that, you get a free lunch. If you don't do that, you still get a free lunch, but you feel more guilty. So this launched in 2014, and so here what is happening is the search engine. So what's happening is our pipeline is running on the Google index, and it's recognizing a bunch of tables that we think are really, really good. Okay, so somewhere in the index, it knows that here's a really good table. Now comes a query in, and in one of the very good results, we're recognizing that there's a really good table. Okay? If we can, and then there's a bunch of other machinery that figures out that this table, or a bunch of rows in this table, actually answers your query. So you look for the critical temperature of krypton, and there's a row in an HTML table that we figured that in the left column it's krypton. We convince ourselves that this is about critical temperature, so we will take that row out of that table, put it high on top, and give you the answer. Okay, that is what we do. And the number of examples goes on and on. This is the example that enabled me to retire with honor from Google. So if you ask for, it's up there, it's top coffee producers, you will get the answer from Wikipedia, which is correct. It's good. The only question that comes to your mind is, I didn't know that Vietnam grows coffee. Second biggest coffee producer in the world. So now you know that. It does grow Robusta, not Arabica, which is why you don't see a lot of coffee shops, telling you that they have Vietnamese coffee. Okay, but that's a detail. Well, it's an important detail. Okay, so I'll move on. These are the people who did all the work. Okay, the now tenured interns up on top. The team below, which actually made the Google search work. And here was actually an important lesson. When we got to this point where our technology was good enough to be part of Google.com search results, what we did at Google, and I write this in my blog, is these three people actually moved from the research team into the search team. Okay. That was the technology transfer. Okay, we didn't throw it over a fence. We didn't sit in our research building and said we'll do it from here. And that was a critical point of this. Now we only did this because it was the right thing for the actual researchers and engineers for their careers at Google and beyond, and they were excited to do this. But this is an important lesson of technology transfer. Sometimes technology transfer means taking it on your own all the way to production. This is the reason we were able to succeed. This may appear like a random comment right now, but at some point in your life you will remember this and say, okay. So that was the HTML tables project. There are a bunch of papers on it at VLDB and similar conferences. But here's one of the problems that came up with HTML tables. I have this beautiful table. This all PhD experts will agree with you, database PhDs will agree, this is really good data, okay? Except if you look at the data itself, at the table itself, you don't know what it is, right? At this point in the talk, you realize it's probably about coffee, but the machine does not know this, okay? So there's a schema, but the schema doesn't actually tell you what it is. It just tells you what the units are, right? And if you look at the text around that table, in this case, you'll see, coffee production in the title, but there's going to be a lot of other text. So you can't just randomly guess that coffee production is the pair of tokens on the page that tells you what this table is about, right? And coffee production is the critical attribute here. If you don't know that this is about coffee production, you know nothing about this table.
Sorry, I have a question maybe related to that, but about the first part. So where is natural language? Obviously there has to be some natural language processing at some point to convert to some kind of, was that something that was already being done as part of the Google search process that you just could use, or was there something special that had to be done to hook into your table, like the natural language with synonyms and with different
Yeah.
all that kind of stuff?
So that was part of the existing infrastructure. So Google does have a very robust, scalable natural language parsing. I can say anything I want about Google right now. They can't fire me anymore. So this is all, everything I'm saying is true to 3 months ago. So hey, if they changed it, I don't know. So Google has a very robust natural language parsing infrastructure that parses basically every document that the search engine sees. Some of that, just one second, is used in interpreting queries. So some of the synonyms, even though synonyms existed even before that was used. And at some points, we actually use some of the parses in order to figure out which parts of the phrase might be indicative of something, even though that's still in the very early stages. But no, we didn't develop any special NLP stuff.
So Google's ad supported, but you're putting the answers to everyone's questions like front and center above any kinds of ads or anything like that. So isn't that kind of counter to their whole business model, or kind of how are they justifying this?
That's a great question. In fact, if you look at the knowledge cards, right, the knowledge cards are exactly where the ads used to be. And somebody thought about this carefully, because last time I checked the revenues of Google, I've actually hit an all-time record. I think I really can't speak too much about this because I don't know, not because they will fire me. But I think it depends on the topic of the query, of what you're going to get. Some of the ads are on the top now, right? So they don't actually, so they're not actually interfering. So they're not on the side anymore, right? So they're not interfering with the knowledge card. But I think the overall philosophy was, it is much better, and this is always Google's philosophy, it is much better to give users good answers than to give them ads. And I think the experience of that just shows that, I mean, if you look at the success of ads at Google, if you follow that philosophy, if you try to optimize for ads instead of good results, you lose.
But if you take this like to infinity, so that you always have the answer to everyone's question, like right off the bat, then there's no room at all, right? Not just in some cases.
That is true. I don't think anybody at Google is thinking of taking this to infinity, except revenues. Okay. No, I mean it's a complicated question, and you can say, you know, if you're asking about the birth date of Fahrenheit or the top coffee producers in the world, is there a good ad to give you? Not really. That's not what you're looking for. An ad, you give an ad when it can possibly answer your information need. That's what. But there's another issue with what you're asking for, which has received a lot of attention at Google, is that if you're always going to give the answer, you might be taking away traffic from the site that worked hard in order to create the answer, right? So essentially what you're doing is you're taking the information. I know you wanted to ask that question, I'll give you credit for it. But you're actually possibly taking away traffic from that site. But that actually doesn't work either, because you're usually bringing more traffic to the site just because people might click there and start navigating. Okay, so we've been very careful with making those choices, and there are different ways in which sites today contribute using schema.org, content that actually gets into knowledge cards. So you can, for example, a menu. So today restaurants actually put their menus in what's called schema.org. It's just a fancy name for structured data. Okay, so if you put it in the right format and somebody queries about your restaurant, you actually might get some of the menu items appear in that knowledge card. That's great for you, right? Because now it's a win-win situation for Google and for the restaurant, because hey, you might actually get somebody to buy your food. That's better, right? So it's a really tricky balance between information providers and search engines. Okay, so I'm going to go really quickly through Biperpedia, but here's the thing, right? So you and I can look at this and say coffee production is what this table is about, and because we know that coffee production is an attribute of countries and this is what it's about, but the machine wouldn't know that. The machine wouldn't be able to recognize coffee production from any other pair of tokens that appear on the page. So my dream was, suppose there was a system that knew all the attributes that countries have. They'd have GDP, and they have monarchs, but somewhere down in place 4,417, they also have coffee production. Okay? And in fact, not all countries have coffee production. Only about 45 of them have coffee production, and you have 220 countries. Okay? And despite popular thought, Italy does not grow coffee. People think Italy grows coffee. Sorry, Carlo. Okay? So suppose you had all the attributes that countries could have, and now you have a simpler problem. Now you can say, well, I see coffee production up there. Okay, maybe I know that coffee production is actually an attribute of, I do know that it's an attribute of countries. I know that it's a number. Now I see a bunch of countries in the first column. Now I have at least more confidence that maybe that pair of tokens is actually what this table is about. But that hinges on having that very broad encyclopedia of all the attributes that countries can have, that people can have, that actors can have, that zoos can have, or that red wines can have. Okay? So Bipedpedia is the attempt to create that or to mine that set of entities from the web. And my argument was, what we do at Google is we often go into a new vertical. For example, somebody decides that red wines is the vertical of the quarter. We're going to go after red wines. We're going to give you a really good knowledge card of red wines. But before we can do that, we need to figure out what are people asking about red wines. Are they asking for the price? Are they asking for the nutrition or whatever? So if you had that dictionary of attributes with some weights on them, then you would actually know how to build this thing. And in general, you would know that a query is actually asking for structured data. Even if you didn't know the answer, it's better than not knowing that it's about structured data. So Bipedpedia is for every class that is identified in Freebase, basically, and a bunch of others. It is a set of attributes, of binary attributes. These are the things that instances of this class have. So countries have GDP, they have firearms experts, which happens to be attribute number 100,000, and they also have coffee production. Okay, so we have what we've been able to do is mine 2 orders of magnitude more schema than what is in the knowledge graph schema. Of course, it comes at a price. We're not clean. We don't have, not all of our schema is clean. And the important thing, which I think is a lesson that is guiding some of the projects we're thinking about at RIT too, is that it's an ontology for search applications. It's a schema, okay? If you think, so this is a schema. This is a schema for the world. A schema is a prescriptive thing. A schema tells you, here's how you need to represent your data. If you don't represent your data this way, I will not understand. That's not what Bipedpedia is. Bipedpedia is a descriptive schema. Bipedpedia is a way of recognizing that a particular set of attributes in a table might be talking about a concept that you do know about, which means Bipedpedia needs to know about all the variations of that attribute. It needs to know about synonyms. It needs to know about misspellings. It turns out that 13% of the queries for structured data that come into the Google search engine are misspelled. Okay, so if you don't recognize those misspellings, you're not going to recognize these things. Okay, it needs to know what are related things that, for example, parent and father are related attributes. You may not know exactly what the relationship is between them, but it's basically, Bipedpedia is supposed to have enough information about these attributes so you can recognize them in the real world when they appear in random ways that people have decided to write them down. Okay, so time-wise, how am I doing? I'm doing very badly. Huh? Okay, so let me get to the end here. Huh? I'll wrap up in 10 minutes. Yeah. So so we essentially what we did was we did some pattern matching on the query stream, okay, which gave us a whole bunch of candidate attributes. We saw how many times they appear, so we knew what the important attributes are and what the less important ones are. And then what we did was we took those attributes that we got from the query stream and we looked for sentences in text that mention these attributes. And then in text, you can actually find other attributes that are not mentioned in the query stream and extract even more attributes. So this is called distant supervision. We got something like over 55% precision. In other words, out of all our attributes, about 55% of them are actually good attributes. Okay, and that led to all kinds of interesting questions as well. But the bottom line was we were able to recognize. So if you look at this table list of largest container ships, we were actually able to recognize what these attributes in this table mean in terms of query attributes. And so we were able to we were able to actually understand a factor of 5.7 times more tables on the web than you could have if you only had the Freebase ontology on its own. And one of the projects we're looking at in RIT is maybe we can actually build a schema like that. We call it wiki schema. Maybe we can build a very broad schema, a descriptive schema, not a prescriptive one, but using humans. okay? And not looking at what people ask on the web, but looking at what people actually model in enterprises and be able to help people in enterprises discover and clean and integrate data sets, okay? So this is a very early project that we're just starting to work on. So I actually want to jump to the conclusion because that's where we want to be. So what I argued today is that, first of all, structured data is a huge thing in web search, and it's only getting bigger. And you know, if you look at the number of engineers that are working on it, it's several hundred engineers just in one web search company I happen to be familiar with. But my point is, in the process of doing that, Google and its peers basically blew away what we know to be the interface to databases, right? I mean, you have more people querying this database than any other database in the world, and you know, all the assumptions about the data, all the assumptions about the query that we always make in databases, was all blown away, okay? And it does a pretty good job, and not a perfect job, but a pretty good job. So, and obviously there's more work to be done in terms of covering more domains and more languages and deeper interactions with the data, so you can actually see the answer and now start navigating the data in a more interesting way. But the point is, while the search engines blew away our interfaces to databases, the enterprises are still stuck in the Stone Age. If you go to any enterprise, it is incredibly difficult to even find what data you have. Okay, who's using it? Can I use it? What are the semantics of it? Is it clean or dirty? What are the underlying assumptions that this was created by, so I can know even if I can use it for something different? It's even Google itself is stuck in the Stone Age in that way. There's a project that we're going to show at Sigmund this year, where we crawled all the data sets we have at Google, 26 billion of them, okay? It's a search engine for data sets within the company, okay? So this was quite an innovative idea at Google itself. And other enterprises are way behind. So the research challenge here, and again, a call to join RIT, is we need to bring enterprises forward to where the world is today in terms of search for structured data. We should be able to pose a keyword query on our internal repositories and find stuff, even find the data sets, not only find the data itself. So if we're going to talk about the data revolution in the age of big data, we got to fix this. Otherwise, we're dropping a lot of data and value on the floor right there. So that's it. Thank you. Theory, when you say theory, do you mean computer science theory as in the mathematical nature of it, or just concepts from research and computer science?
No, I mean theory in the mathematical sense. The mathematical theory.
Yeah. I think there's room for theory. So in particular, if you look, one of the problems that I've been struggling a lot with during my time at Google is if you're trying to figure out whether puppies are cute and rats aren't, okay, you can count the number of places on the web that say puppies are cute and the number of times that say rats are cute, or maybe rats are not cute and puppies are not cute, and you can maybe do a majority voting that that will give you the answer, okay? But the problem is that the web itself is not a mirror of reality. When people write things on the web, they have biases. So many more people will write about puppies. Many more people will write that something is cute rather than something is not cute. So when you look at the number of facts that appear on the web, there is a process. There's a bunch of probabilistic steps that happen on the way to that enable you to interpret that number in a different way. Okay, so how do you model what is the probability that somebody will actually write something on the web with the count of the number of times that it appears? So I think a lot of the work on information extraction on the web just assumes that every fact on the web is independent of each other. That's where theory can help a lot.
I'll give you only one example. You talk a lot about schemas. Do you know anything about the mathematical theory of schemas?
In the presence of Carlos Agnolo, I cannot say yes. But between the two of us, we. Right.
A question about the truth store. So Google's truth knowledge database is closed. Is there some concern there about the disproportionate authority Google might give to a fact by saying it's true? And for instance, just today, Wikipedia's Mythbusters cracked what they think to be the oldest myth in Wikipedia history, a page that lasted 10 years without anyone realizing it was a fake person that never existed. There's none of that peer review process for internal Google storage. True.
Well, so there's corroboration. So there are facts that people look at them to see whether they can be found from independent sources. So I mean, yeah. So that's basically what Google does. As I said before, it's not the same thing as guaranteeing truth, real truth, but it's a pretty good approximation. And these are humans, so if it's really something ridiculous, they will notice even if it's corroborated by 3 facts.
Is there any thought of opening that up? People can get it directly?
Probably not, because it's an asset. It's an important asset that Google and other companies spend a huge amount of effort. Not only that, some of the content in the Google Knowledge Graph, I would imagine, is purchased from other providers, and legally they can't open it up.
Any concept of back propagation? I see something, I think it's wrong.
Yeah, there was something. So there was for a while, you could actually give feedback on facts. I don't know if it's still there. Huh? Yeah. Yeah. There was a project called Knowledge Vault by Evgeny Gabrilovich and Luna Dong, where they try to. So the problem, right, is Google has to throw out a whole bunch of stuff because they don't have the confidence above 90 something, right? So what that project tried to do was let's keep around the stuff that we're less confident of, and maybe later we'll find additional evidence that will boost up the what we think is the likelihood of it being correct. Because a lot of the stuff that was being left on the table was actually correct. It was just not a way of verifying it to the standards that we needed. You got a question? That's a great question. It's been a dream of mine. Look, I mean, the data at Google is in graph. It's in a graph data model, which means you can traverse edges in the graph, which corresponds sometimes to, if you were to store this as tables, this would be a join. Okay, so essentially what Google is doing is it's materializing some of these edges, these joins by paths in the graph. So they try to do a good job at figuring out that the word uncle is brother of mother or brother of father, okay, and giving it a one-word thing, but nobody's, to the best of my knowledge, nobody's doing a real join right now. I mean, they do filters, they do, I don't think, huh? There is, for stuff like that, what they will try to do, and this is actually the same web tables team, they had some, if you ask for the largest, they will recognize that the query is asking for an aggregate, like largest or smallest, and they will try to find a table that has that ordering, so the table is already, the HTML table already gives you the answer the way you like it. Now these are hard things. I mean, that's why I think, you know, we're just, I think Google and its peers are scratching the tip of the iceberg on structured data. But it's really exciting to see it. You can try it. Okay, thanks.